of algebra as far as rational numbers are concerned. We will now proceed to do so without further comments. So having this proposition, we are now all the rules of algebra are available to us and we will freely use them without saying anything. Why? Without justifying their use. Okay, so the next thing we are on to is the categorization of rational numbers into positive, negative and 0. Just like how we categorize integers into positive, negative and 0. So we are going to do a similar thing with rational numbers. And that is done in this definition. This is definition 426. A rational number x is said to be positive if there exist positive integers a and b such that x is equal to a by b. Note that now this a by b is meaningful. We know what it means. X is said to be negative if x is equal to minus y for some positive rational number y, that is x is negative if and only if there exist integers c and d where c is negative, d is positive and x is equal to c by d. From this definition of negativity of a rational number, we can get an equivalent definition which is very easy to see. If x is negative in this sense, then such c and d will exist, and conversely if c and d exist, then x has to be negative. Okay. Thus, for instance, every positive integer is also a positive rational number. is also a positive rational number. Why? Because you see, if you take a positive integer a, then according to the identification that we have made between integers and some rational numbers, this can be written as, this is equal to a by 1. No? If you want, for temporarily, let me use this notation, a by 1. So this rational number is expressed in the form a by 1, where a is a positive integer and 1 is also a positive integer. So as a rational number, this integer is also a positive rational number, and originally it was a positive integer. So the categorization of rational numbers into positive, negative and 0 is consistent with the similar categorization for integers, and we will write like this. And every negative integer is a negative rational number. Okay. So our new definition of positive and negative is consistent with the corresponding old definition. So this identification not only preserves the algebraic structure, that is, it keeps the operations of addition, multiplication and negation similar in a precise sense that I am not going to talk more about right now, in the sense of those identities, that if you use a or a by 1, you are going to get basically the same thing. But it also keeps positivity and negativity intact. Whether you think of a as an integer or as a rational number, if it is positive, this is also positive. If it is negative, this is also negative. So in that sense, the two definitions are consistent. Okay. So after that, we have this lemma. We had a similar result in the previous section for integers, trichotomy of rationals. We had to, oh, I forgot the number. Let me write it here. 4 to 7, which you already can expect what is going to come. Let x be a rational number, then exactly one of the following three statements is true. A, x is positive. B, x is equal to 0, and C, x is negative. And its proof is an exercise. It is going to be very easy. See exercise. So we will handle this in the exercise itself. 4 to 4. Proof is easy, but nevertheless a proof is needed anyhow. Okay, now having this definition of positivity, negativity, etc., we are now ready to define an order relation on the set of rational numbers. So this is the next and the last definition of this section, 4 to 8. Ordering of the rationals. Let x and y be two rational numbers we say x is less than y, or you can also say x is strictly less than y, denoted by this or this. If x minus y is a positive rational number, we write this or this. If x is less than y and x is, this is, I forgot, in the, when we defined the order relation on the integers, we first of all defined less than or equal to relation. Here, however, we have decided to define the strict relation first and then this one in terms of the strict one. If x is less than y or x is equal to y. Okay, tau has defined y less than x also separately. Is that actually needed? Because this part itself covers that. We say x is less than, if you have y less than x, then that would mean that x minus y is a positive rational number. So I am not making that a part of the definition. Then finally we have the proposition which states the basic properties of this order relation. This is proposition 4 to 9. Basic properties of order. On the rationals. part A. Just like the one for integers, this has some parts. Part A is order trichotomy. But before we write this, there is one more line. Before we have the parts, let x, y and z be rational numbers. Then the following things are true. Exactly one of the following statements is true. X is less than y, y is less than x. We should not write or, because we are writing three statements. Now x is equal to y. So this is order trichotomy, which will follow directly from that lemma that we had before. Trichotomy of rational numbers. B, part B is order is antisymmetric. In the actual text, Tao has made a mistake. He wrote something that does not make sense. That's not what antisymmetry means. So the correct statement is this: if x is, or since we are writing less than or equal to more often, so let's use that. X is less than or equal to y and y is less than or equal to x, then x should be equal to y. Then order is transitive. If x is less than y and y is less than z, then x is less than z. The next, so these are properties of only the order relation. The next two parts show us how order relation behaves with the algebraic operations. Addition preserves order. If x is less than y, then adding z on both sides does not change this inequality. Like that, positive multiplication preserves order. If x is less than y and z is positive, then xz is less than yz, and its proof is also an exercise. This is the fifth exercise. And finally, there is a remark. This is remark 10. And I am going to write exactly what the author has written. The 5 properties in the above proposition combined with the properties in proposition 4 to 4 have a name. They are asserting that the rationals Q form an ordered field. So if we combine all the properties that say that the rationals form a field, namely the laws of algebra for rationals, along with these properties of order, then together all these things are saying that the system of rational numbers is an ordered field. Or if I say is an example of an ordered field, then that would mean that there are other examples, and that is true. In mathematics, there is a general concept of an ordered field, where we have a field on which an ordered relation has been defined, for which properties like this are true, and they are studied. So with this, the text part of this section is over. Next we will move to the exercise problems.